All right, so here's our note sheet, and our topic here is percent ionization. Percent ionization is another way to describe for a weak acid or a weak base how much of them uh, how, are making the hydronium and the hydroxide. It's like a percent yield. It's typically a smaller number, and it gives you a gauge of that's a little more tangible about how much is actually breaking up into your respective ions. All right. So when I put a weak acid and a base into a solution, all right, some of it will dissociate, all right, and percent ionization is going to tell you how much of that it is, all right, and you can see Dr. Square is saying 20%, 1 in 5, all right. As like a definition, you could say how much completely. Here's a definition, all right. It's much like percent yield, where percent yield tells you how much you make of how much you should have made. All right. This is another percent comparison. Here is our formula, and it would be OH negative and B for the base. All right. And that stands for initial and equilibrium. We've got some 0.5 molar citric acid. All right. How much of it is actually dissociating? How much of it is separating into its respective ions? In this case, it'd be H plus and the citric anion. Here is citric acid. You can see it's a pretty cool molecule. And what you're going to need to do this is you're going to need the Ka value, because the Ka value is going to allow you to calculate your percent ionizations by calculating your equilibrium concentration of hydronium or hydroxide. Now we're going to need a Rice table, and we're going to need an equation. So citric acid is an acid, so it's going to give a proton, these ones in the front, that's going to change to a 2. It's going to give a proton to water, and I'm going to have that. All right. And then I'm going to set up my Rice table, my ice table or rice, whatever. 0.5 molar, none at the start. I'm going to add some, minus some, get this. All right. So there's my ice table. And then here's my equilibrium expression from that. And then I just simply multiply this by 0.5. That's going to be 3.7. Take the square root. And X is going to be that. That's my concentration of hydroxide in this case. And then I need to remember that this value, right, this 0.193 stuff is for the hydronium. So that's like how concentrated I am with hydronium, all right? And that's its molarity, all right? I want to know really though, what's the percent ionization? How many citric acids actually separated? So I remember my formula, this one, all right? And then I plug that this into that formula and the 0.5 molar for the initial concentration. So that's going to look like that, all right? And that gives us a whopping 4%. So 4%. Now what that would mean is I would need to draw one more hydronium, and I can't find my pencil, and then 96 dots, all right? I'm not going to draw 96 dots, all right? But that's what it would look like. Now, there's an There's an interesting trend with ionization energy at a higher molarity. Let's just say I did 1.2 citric. All right. Here's my ice table. There it is. All right. That's what I'm going to get. And this would be 1, 2, and that would be X. And this, and oh, I forgot to mention, we're going to neglect the X because in AP, you're not going to have to solve on a quadratic. And then what am I going to do? I'm going to plug that in, and I'm going to take the square root of this and plug it back in and multiply that by 100. That says 100, and I get 2.5. So you'll notice I increase the molarity and my percent ionization goes down. So at higher molarities, the percent ionization decreases. It's an inverse proportion. All right, thank you. Hope this helps.